So here we are with our last assessment of directing and figuring out whether deactivators or activators favor what position. In this situation, we're looking at halogens. These are weak deactivators, so they still will slow down EAS reactions. Halogens are highly electronegative and they pull electron density away from things, and it only makes sense that they'll try to pull electron density away from the aromatic ring. Again, that pull of electron density inhibits the ring from behaving like a nucleophile since it needs electrons to attack, and that will slow down the ring. However, halogens behave a little differently than other deactivators, and we have to assess to figure out whether it's going to be ortho, meta, or para. So with all the talk I've gone through about figuring out what positions deactivators are at, you could probably take a guess that it's not going to be meta here, and let's see why. So again, to start out, we draw resonance. Resonance, resonance, resonance for these problems, right? If you weren't good at it before, you will get good at it now. Alright, so we're still drawing resonance for our ortho group. Okay, and you may want to stop here and you'll say, well, again, we're positive charge on that carbon bearing the deactivating group, and you may say this is unstable. However, the halogens have lone pairs of their own, and it's only makes sense that you should probably see if something has a lone pair next to a carbocation or attached to a carbocation that it tries to help out and support the carbocation. And that's what we see happen here. Okay, and so the Br ends up taking on the burden of the positive charge as well within the ring and helping to stabilize that positive charge through resonance. So ortho has 4 resonance structures. Let's assess meta. Alright, and so what we see here is that meta only has 3 resonance structures, and that's because the positive charge never lands directly on the carbon that has the halogen. So the bromine in this situation can't help support and further stabilize that positive charge. Lastly, let's look at the para position. And so one more time, what we're going to see is this bromine being willing to help support the positive charge by forming a double bond with the carbon there. Positive charge on the bromine. I know it looks weird, but it happens. And we have to do the last resonance. If you can't jump twice like that, and you have to do it by one step, that's fine. Just realize you're remaking the same resonance structure and don't count it twice through this process. So don't tell me there's 5 resonance structures on para. There's only going to be 4. So again, ortho and para, same situation. You get 4 resonance structures. Meta, you only get 3. And since I've always talked about resonance being a stabilizing factor, the major products for this reaction are going to be ortho and para. Okay, so ortho and para are the favored products, the major products for these reactions, And they're still deactivators. They're still slowing down the reactions. But halogens will favor ortho and para substitution.